We will now have a discussion on the energy in a mechanical wave. As you might know, the mechanical wave can have two modes of energy position. One, the kinetic energy due to the motion of the wave through the mechanical medium. And the second one, that is the potential energy resulting from the deformation of the medium. If it's a stretched string, there will be a deformation for the string. If it's a wave propagating through water bodies, then the level of water bodies will be varying. This account a deformation for the level for water surface. This can account for a change in potential energy, and motion can attribute kinetic energy for the wave. So the evaluation of the energy of a mechanical wave is essentially the evaluation of the kinetic energy part and the potential energy part. We will first of all evaluate the kinetic energy part. For that, consider a string of length, say dx. As you could see, this is the length dx of the wave, of the string, and as a consequence of the propagation of the wave through the string, there occur a deformation such that ds represent the actual deformation for the string upon the movement of wave through that string. So ds is the actual path followed by the wave, or this can be taken as the deformation for the string of length dx. Let mu be the mass per unit length of the string. Often this is referred to as the linear density, and depending upon the nature of the wave, we will have to define three different kinds of densities. If the wave is one-dimensional, we will define the parameter referred to as the linear density, which is the mass per unit length, and in a two-dimensional wave, the parameter defined will be mass per unit area, which is referred to as the areal density. And in the case of a three-dimensional wave, we often define the parameter density as such, which is the volume density, mass per unit volume. In this case, we have a string of length dx such that the linear density defined is mu. Then the mass of the length dx of the string will be mass per unit length mu into length of the specimen, that is dx. And the transverse velocity, that is the velocity with which the wave is propagating, which will be essentially the change of y parameter with respect to time, that is dy by dt, and it is this y parameter that will be often represented in a wave, as you have seen earlier. Then the kinetic energy of this much length, say dx, will be equal to half into mass of the specimen mu dx into velocity square. Velocity is dy by dt, so dy by dt whole square. Often we define a parameter referred to as the kinetic energy density, that is the kinetic energy per unit length, as long as a one-dimensional wave is taken into consideration, and you will have the two other aspects of kinetic energy density corresponding to an areal propagation of wave as well as a volume propagation of wave. For the time being, we have this parameter, that is kinetic energy per unit length, which is essentially, say, dk by dx, that is equal to kinetic energy half mu dx dy by dt whole square divided by dx, such that dx vanishes and we will have kinetic energy density half mu dy by dt the whole square. Now we will evaluate the potential energy, and of course the potential energy density. The potential energy has only one choice as long as a mechanical wave is taken into consideration. This arises from the extension of the string upon deformation or upon the propagation of the wave. When the wave is propagating, there occurs an extension for the length of the string that account for a change of potential energy. It is that parameter we will have to now evaluate. Now this potential energy will be equal to net force acting on the specimen, which is nothing other than the tension on the stretcher string into deformation. We have labeled the tension using this symbol, say T, and the deformation will be ds minus actual length, that is say dx. And from this diagram you could see that ds is the hypotenuse of a right triangle whose altitude is dy and base is dx. Then ds is essentially square root of dx square plus dy square. So we have ds equal to square root of dx square plus dy square. or that is raised to half, which is essentially the same thing. And we can take dx outside to make it say dx into 1 plus dy by dx the whole square. Dx is taken out from this, out of the square root as well. So dx come out from this term, 1 remains, plus dy square divided by dx square, that is dy by dx is whole square raised to half. Here we can have a binomial expansion for this term. This is essentially equal to dx into binomial expansion for this is possible once dy by dx whole square is extremely smaller. For the concerned length, say dx, which is infinitesimally smaller, dy by dx is extremely smaller, such that we can have dy by dx as an extremely small parameter. Its square will be further smaller. This is true. For any value less than 1, you know that the square, cube, etc. will be falling very rapidly, and for any value greater than 1, this square, cube, etc. will be increasing very rapidly, and for 1, the square, cube, etc. will be the same, or that remains unchanged. So we have here a possible binomial expansion. Dx is taken out. Dx is taken out and dx into 1 plus x square whole raised to half is 1 plus half into x square. 1 plus x square whole raised to n is 1 plus nx plus nc2, and that is n into n minus 1 over 2 factorial into x raised to next power, etc. Since dy by dx is extremely smaller, the higher order terms can be neglected, and we have the term up to the first order that make it say 1 by 2, 1 divided by 2 into dy by dx the whole square. So we substitute it here. Then ds minus dx becomes dx into 1 plus ds into 1 plus half dy by dx square minus dx. So dx term goes, what remains is half into dy by dx whole square into dx. This dx comes from the outside. So we can have an expansion here. This is essentially dx plus half into dy by dx whole square into dx. That is ds. Then ds minus dx will be, you have a minus dx here, dx goes, what remains is half into dy by dx whole square into dx. So ds minus dx is half into dy by dx whole square into dx. Such that the potential energy, which is say T into ds minus dx, is T into ds minus dx is half into dy by dx whole square into dx. To make it say half T into dy by dx whole square into dx. Then the potential energy density, that is the potential energy per unit length, will be, you have to divide this by means of dx. So dx vanishes. What remains is potential energy density du by dx equal to half T into dy by dx the whole square. Now we could prove that the potential energy density and the kinetic energy density in a mechanical wave are exactly equal. We have already obtained two empirical relationship for this. We will now see that these two energies are exactly equal, and that will be contributed towards the total energy. Since we have only two modes of energy possession, these are kinetic energy and potential energy, then the total energy will be the sum of the kinetic energy and the potential energy. And we have evaluated the kinetic energy density as, say, dk by dx equal to half mu into dy by dt whole square, where dy by dt is the velocity. Potential energy density is half T into dy by dx whole square, where T is the tension on the string. Now we will prove that these are exactly equal as long as a mechanical wave or any wave is taken into consideration. This we have proved several times. In the case of a harmonic oscillator, which can also be treated as a kind of periodic motion in a mechanical medium. For that, consider a traveling wave in a stretcher string. This generally follow an empirical relationship of a periodic function. We take it off and say y, which is the displacement from the equilibrium position, which is a function of x coordinate, and the time coordinate will be a mathematical function which is periodic. And a periodic function will be represented as a x plus or minus v into t, where v is the wave velocity. We take this parameter as say z, or this variable as say z, such that the wave motion can be mathematically represented as say f of z. Now again we know that the wave velocity v is equal to square root of t by mu, which is the expression for the velocity of a mechanical wave in a solid medium, where t is the tension on the medium. That is say square root of t divided by mu. Now look at this mathematical function, say f of z, dy by dx, which will be required as long as the potential energy is taken into consideration, and dy by dt, that comes as a parameter which is velocity in the kinetic energy density. So we will evaluate say dy by dx. dy by dx is d by dx of say f. That is a function of x as well as vt. When its derivative is calculated in terms of x, we assume that it's constant in t, such that derivative of f of x plus or minus vt with respect to x is derivative of f, that is f dash of z, into derivative of x. This needed to be treated as a function of function. Derivative of the first function into derivative of the function within it. Derivative of the function f is f dash into derivative of x with respect to x is 1. So dy by dx is f dash z. Now dy by dt, derivative of f with respect to time, that is f dash derivative of f into derivative of vt with respect to time will be plus or minus v. So dy by dt is equal to plus or minus v f dash of z. F dash of z. Now substitute these values of dy by dx and dy by dt in the expression for the kinetic energy density and the potential energy density. Then we substitute dy by dt as say v f dash of z. Square of plus or minus v is essentially v square. So kinetic energy density becomes half mu into v square into f dash z whole square. And the potential energy density half t into dy by dx whole square will be half t into, that is half t into dy by dx is f dash z. Dy by dx square will be f dash square. Now we substitute from this expression t equal to mu v square. Substitute t as mu v square, then this becomes half mu v square f dash square. Half mu v square f dash square, which is the same as the expression for the kinetic energy density, half mu v square f dash square. So we prove that this is also equal to half mu v square f dash square. And we conclude that the mechanical wave can have two modes of energy possession. These are kinetic energy density and potential energy density. Both are exactly equal and found to follow an empirical relationship, half mu into v square, such that the total energy density will be half mu v square f dash square plus half mu v square f dash square, that is 2 into half mu v square f dash square, that is equal to say mu v square f dash square. This expression we prove or we calculate in the case of a sine wave, that we can do in the next video.